All right.
Should.
Well, this is the rub salt on wound session, so it might sting a little bit. But it does help prevent any further decay. Your wound will be clean after this. All right, so let's go to the class. I have all the questions uploaded too, so in case anyone is interested in what are the variations of each question, it is all in this archive file. So that's a pretty typical thing that I do. I just make variants of the same questions, maybe 3 or 4, for each question, and then each person will get, a random pick. I don't even know, the pattern because it's all generated randomly. That's why I cannot send my files to the print shop, because the print shop will print the same thing, X many times. And this, I have a special program. PrintQ is the Python program that I use to print out the exams. So that makes grading interesting too, because the quote unquote correct answer is not always going to be the same. But they're close enough, so I can look for a general pattern. All right, so let's take a look at the first question. And by the way, this is a really nice program. If you don't know it already, it's called Zerno. It allows you to open up PDF files and also annotate in the file. In other words, it's kind of like Adobe Acrobat, but it's free. It's open source. So it's kind of nice and cool. Okay, let me magnify just, too much. Okay, yeah, not enough. View, zoom, set zoom. Okay, I think 125 would probably be good, yep. Okay. All right, this is question 1. Yours may not look exactly the same as this one, but it will be very similar. Okay, this one is the reverse of the similar question. I think it's also question 1 in the practice exam. In the practice exam, I give you the instruction with a complex addressing mode and ask you to turn it into RISC instructions using simple instructions. This one is exactly the opposite. I give you a sequence of instructions, and then you have to replace the sequence with a specific instruction or with a specific addressing mode so that you can accomplish the same thing with fewer instructions in this case. So let's take a look at the first part. There are 2 parts, and definitely there'll be partial credit. If someone answers one correctly but not the other one correctly, there'll be partial credit because these 2 are independent. They don't depend on each other. All right, so I'm going to use a red pen here. The first part consists of these 2 instructions. And I want you to replace these 2 instructions with a single instruction in the blank space given here. All right. In the first instruction, we have the move L instruction. It has a immediate operand L1, and then moving that into EAX. In the second instruction, I move indirect EAX to EBX. So the question is, if I am allowed to use cisp type addressing modes, how can I replace this with a single instruction? The destination operand cannot be changed. EBX has to be there in the final instruction. So your only option is to change the first operand. And this one, because the first one starts with an immediate L1 into EAX, the second instruction uses EAX as an address, and then it goes to that location to grab the content and then copy the content from memory to EBX. In other words, it's doing what a direct operand is doing. This one really should not be too difficult because it is also used as one of the examples when I illustrated the direct operand in the book, in the text. So the answer to this question, to this particular one, if I use a text tool here, and I can use mono space, 12 point, okay, I think that would be good. Okay, so the answer is move L1 without the $, without parentheses, just L1 by itself to EBX. Are there any questions about the first part? Yep.
My test says move indirect EAX into EAX.
Then it becomes EAX.
Okay, just making sure you notice that.
Yeah, there are 4 variants.
You got it. Oh.
Yep. Mm-hmm.
So the first instruction moves the address of L1 into EAX?
I wouldn't call it that way. You know, the first instruction moves whatever L1 is. L1 is a label.
Right.
And a label has a definition that is an integer of some kind. It can be 0, can be 500, can be an address. We don't care what it is. So in this case, what it does is whatever L1 is, it moves that value into EAX.
I'm having a hard time seeing the difference because when you declare a label, it's a bookmark somewhere in the program.
Not necessarily, because you can say L1 equals 16. In that case,
You can
L1 is
change it.
defined as the constant 16, nothing more.
Okay. But in the typical usage of a label, like to reference a particular part in the program, it is an address. And so the immediate value moves the address of the label.
That integer can be used as an address, yes.
Because that's the way I understood it. Like it moves if you just wrote L1 like the answer is, it references where L1 is and then the value at L1. But if you have the $sign, the immediate value, it references the address, which is why when you use the EX with the parentheses, it uses that as an address to get the same value.
Okay.
Does that sound at all correct?
It is somewhat correct, okay, but because you're still referring to concepts that you learned in your C++ class. The concept of L1 is an address comes from the C programming class. From the perspective of the assembler, L1 can be defined to anything. It doesn't really matter because all we're doing is if you see the $sign as in the operand, all it does is to evaluate the expression next to the $sign. It can be a constant, can be a huge big expression. It doesn't matter what it is, but whatever the expression evaluates to becomes the value of the operand.
Would the program still? It doesn't seem to me like move L1. That translation of that instruction would work unless L1 was interpreted as an address by the immediate operator.
Well, if it is not, it would just crash.
Okay.
But these 2 instructions will still be equivalent to this one single instruction. The question is just asking, give me one instruction to replace those 2.
Right.
It doesn't matter whether it is going to crash or not. In other words, if I use $0 here, then you just have to write 0 here, even though knowing that this instruction most likely will crash.
Okay.
But it will still be doing the same thing. You still need to make sure that your instruction is equivalent to the 2 given instructions. So what you said is about right, but you're still thinking in high-level programming terms, and that can, bite you later on. Okay. So you just have to be careful and try to think from the perspective of the assembler and also the processor, rather than high-level programming concepts. It's a good way to transition into assembly language programming, but thinking too much in terms of a high-level programming language can lead to problems later on. Okay. Okay, the next 4 instructions look kind of tricky, but they're not. Okay, so let's go ahead and take a look at these 4 instructions. The first instruction, all it does is to copy EBX to ECX. The second one doubles the value of ECX, and ECX at this point has the value of EBX. So ECX equals 2 times EBX at the end of the second instruction. And then we add L1 to ECX, and then we move indirect ECX into EAX. Okay, so if I were to comment each and every single line, I know it's kind of confusing here because I have the other one at the wrong place. Okay, so in the first instruction, we have ECX equals EBX. In the second instruction, we have ECX equals 2 times EBX because we are doubling the value of ECX. So ECX ends up to be twice the value of EBX. Is that okay? Does everybody understand how after the second instruction ECX is twice EBX? Okay. And the third instruction is just adding L1. So ECX becomes L1 plus EBX times 2. Is that okay? And then the last instruction is moving indirect ECX into EAX. So the question is, if I want this to be my effective address, how do we use a single operand to do it? And the solution is move L. L1 is on the outside because the constant always go to the outside. Do we have a base register here?
No.
We don't have a base register. Just specify a comma in, to say that there's no base register. Do we have an index register? Yep, the index register is EBX because we also have a scale. What is the scale in this case? 2. The scale is 2. That's it. And of course, you also have to finish up the instruction by providing the second operand, which is just copying from the original instruction.
So what if I only have the first part, but I forgot the dot, the percent sign EAX? You know what I mean? Like I only have the L1. I only write the L1 parenthesis, comma, EBX, and 2. That's it. Is that going to be okay?
Well, the assembler probably won't take it,
I know.
so you will have partial credit in that case. Okay, there's actually an alternative here. Okay, there are actually 2 alternatives in this case. One alternative is I think I forgot certain things here, so let me go fix that first. I forgot the percent symbol. So I would not have gotten perfect score in that case because I forgot the percent symbol. Okay, so this is the second alternative is like this. It works the same way because you're using EBX as a base register and also an index register with an implied scale of 1. And there's one more alternative in this case. Don't you like the ones with all the alternatives? That means you can get it right like 3 times in this case. There are 3 chances of getting it right. You can have EBX, EBX 1, because if you don't specify the 1 here, the scale of 1 is implied. It's the default scale. So if you specify the scale as 1, hey, no harm is done. It works the same way. So all 3 variants are accepted as perfect answers. Yep.
All right, this might sound stupid, but I got the right answer. I just forgot to put the move L in front. How much do I lose?
Yeah.
If you forget just to move L, you will still get dinged, like 1 point out of 10 or something like that. It's not going to be a heavy, ding, but it will still be a, kind of like a minor ding. Yep.
Would you be able to use L1 with an ID operand as the base operand?
Using L1, no, you cannot move L1 inside the parentheses, unfortunately.
Okay. Why is that?
Because that's what the assembler language specifies.
Okay.
Inside, it has to be registers.
Oh, they just all have to be registered?
Yeah, only the base register and the index register can go inside the parentheses. The constant displacement has to be outside.
Okay. And for this, the constant displacement is
L1
the value at the address and not the address?
is L1. L1 is the displacement.
Okay, so L1 as a displacement would be the address that L1 is.
It's basically just adding all the components up in this case. So L1 and twice EBX are added up before that is treated as an address. Okay. Now, how many people read the? So let me save this first, and then I'll kind of point out certain things that you can watch out for next time. So I'll go ahead and save this into today's folder. If anyone reminds me to upload this, I will also upload this, and you can download Zernal for Windows. Also, then you can open up these documents and actually see the content. It's really handy. You can use it for any class. I mean, any classes that you take with PDF files, you can use Zernal to annotate the PDF documents. Yep.
Does this do pretty much everything that Adobe does or more?
Probably not as much, but it supports annotation, so it's cool for that purpose.
And then you can open any file, right? Any
You can-
PDF files?
What?
Any kind of PDF file, right?
I have not found a file that it cannot open.
Okay.
That may be some that it cannot open. Yep.
With the instructions, is that we're replacing the previous 3 lines, so would you be able to use?
Actually, it's the previous 4 lines. I changed that, in the class. I, fixed my mistake in the class. You didn't see that? Oh
No. I came up and asked you what.
Hmm?
I came up and asked
Yep, you came and asked me about it, and then I wrote it on the whiteboard. So if it is in the first 3 instructions, then it will be ECX, I guess, because it doesn't refer to E. You cannot link it to EBX anymore. Did you just say 2 of ECX?
Yeah.
Okay, I will consider that as a partially as a correct answer too, because I wrote incorrectly here the previous 3 instructions.
I did the same thing,
Yeah.
except I used both EBX and ECX because you assigned them.
Okay,
Same thing.
I'll take a look. Yep.
Can you consider it all one program because the way you have it all done? So like you already have EBX is defined as L1 previous to that. So it would actually be that last line 3 L1.
This one here.
Yeah. So if you go up to the top of those 4 lines, it's already defined above that. See where you have ECX
Oh, I
equals
see.
EBX? Yeah, yeah.
I did that myself.
So you have L1 in there, so you have 3 times that.
Well, this one is specifically asking to replace the previous few instructions.
Right, but it's actually, those few instructions are all part of one program that's already defined. So you're actually just replacing those with another. You see what I'm saying?
Because you can still look at the previous 4 lines, but interpret EBX as L1 at the juncture and then write it.
You have it
Right.
all commented out like it's a single program.
I will take a look at it and see, because doing that is actually harder than doing this.
Yeah.
So if it looks to me that you definitely get the concept of doing this too, then it will still be okay. But the instruction is only asking for the 3 instructions before this. So
Because I think, I'm not an expert, but you could kind of just figure it out the same way at the bottom.
I mean, okay. So I will have to take a look at all the alternatives first.
I goofed today, but
But it's good that you let me know now. Otherwise, I look at the solution and go like, nope, this is not what I'm expecting. Okay, question number 2. Question number 2 is. Okay, this is question number 2, which is also the reverse of a similar question in the practice test. In the practice test, I give you a multiplication, and then you have to figure out how to do it with just addition and move. In this one, I give you the move and the addition. You have to reverse it back into just a multiplication. Okay? I think this one is not too bad. I think most people get it. So we'll go ahead and find out what each line is going to do. And basically, it's just a matter of tracking down every single line and make sure that you can relate the final value of EAX to the original value of ECX. That's basically what you need to do, is to keep track of everything and make sure that you don't lose any details as a process in the process. Okay, first instruction. For the first instruction is just making a copy of ECX into EBX. So we'll just say EBX equals ECX. Okay, nothing more than that. And I think this font is too big. I will change to a smaller font. Okay, line 2. Line 2 is adding EBX to EBX. So that's doubling EBX, right? So I should actually specify this in a different way. Okay, EBX is twice of ECX. Are we doing okay so far? Because we doubled EBX, and EBX got its original value from ECX, so it actually has twice the original value of ECX at this point. Is that okay?
Yep.
Okay, and then we double it again. So EBX this time equals 4 times ECX because it got doubled again. And then this one is a move instruction, so this is not doubling. I'm just saying that EAX at this point equals to EBX, which also equals to 4 times ECX at this point. So remember to relate all the way back to ECX. The next instruction is going to add EBX to EBX again, so EBX gets doubled, and it becomes 8 times the original value of ECX. And then we are adding EBX to EAX again, so EAX is now 4 times ECX plus 8 times ECX. I'm not even bothering to simplify at this point. I'm just going to write out the entire expression. And then we double the value of EBX again. EBX equals 16 times ECX at this point. it gets doubled again, EBX equals 32 times ECX, and then it gets doubled again, so EBX equals 64 times ECX. And then we add EBX to EAX again, so EAX is 4 times ECX plus 8 times ECX plus 64 times ECX. And then we have one final instruction to double EAX itself. So if you double EAX again, that means it becomes 8 times ECX, which came from the 4 times. The 8 times becomes a 16 times, and then the 64 times becomes 128 times. And if you simplify everything, it becomes ECX times a constant of 8 plus 16 plus 128, which is I'll take that as a perfect answer. That is perfectly fine. There's nothing wrong with this.
152.
And the 52, whatever. if anyone tracks everything correctly and up to here shows this number, shows this expression, and then ends up with a wrong answer anyway, we'll still get most, if not all, of the partial credit.
What if you just did something totally stupid, added like
what?
9 to 64 and got 53? Just totally random.
Then I would recommend send you back to remedial arithmetics. No, just you'll still get most of the partial credit. The key is to show me the work and not to only have the answer here being wrong. You have to show the work. As long as you show the work along the way, and I understand that you know when to relate EAX to EBX and also get to the original value of ECX, it will still be okay. So are there any questions about this one? Yep.
Is that the answer for all the versions?
No, there are 4 variants of this one too. So they're all a little bit different, but they have the same type of instructions. It's just the sequence is off a little bit. The tab points, if you will, out of the shift operation, they all tap a little bit differently. So they'll be pretty close.
Do you have a key with the 4 possible solutions per set, so maybe you could know if we're within the set?
I don't have the key for all of those. So for grading purposes, when I look at it, I will work it out, and then I know how to grade it. If you guys want the key, I can disclose the key. When after the grading process, I can just disclose that. That's fine too. All right. So question number 2 is done. Let's move on to question number 3. This is question number 3. Question number 3 is basically a flag question, but only for add. Okay, only related to add in this case. All right. So the question is very, very short. I give you 2 instructions. Move B 173 to AL, add B dollar, some unknown value to AL, and I want the end result of this to have the carry flag being a 1, the overflow flag being a 1, the sign flag being a 0, and the Z flag being a 0. Okay? Well, the first question is the combination possible? Because it says in the question right there, if the combination is not possible, you have to tell me that it is not possible and explain why it is not possible. This is after we talk about the solution to the flags homework assignment. So anyone who brings along the solution to the homework assignment will know that this is in fact possible. Okay? So the question is, how do we make it happen? Okay. So how do we make it happen? The first thing you want to do is to understand what is 173 as a decimal number. Okay? So we want to convert 173 first into a binary representation, because that's all that the processor looks at are zeros and ones. They don't look at the positive, negative, and stuff like that. It's just bits. So the first thing you want to do is to convert 173 as a binary number. There was 1 or 2 people without a calculator that can do binary conversion, and I let them use the calculator that I have here on the computer. It's not a problem. Did anyone get slowed down because your calculator has no binary conversion?
Mine didn't. I just did it by hand.
You can do it by hand pretty easily. Okay. So let's go ahead and do this by hand first, because I do want to make sure that everybody knows how to do this by hand. Okay. So in this case, it's 173. It's 128 plus. There's at least a 32. And then there's a
8, 4,
8,
and a 1.
4, and 1.
8, 4, and 1. Okay. So that means as a binary number, okay, 0B. There's 1 for the 128, 0 for the 64, 1 for the 32, 0 for the 16, 1 for the 8, 1 for the 4, 0 for the 2, and 1 for the 1. And we should have 10 bits, and that looks right to me. I can also do a quick check here, because I can also look at this as a hexadecimal number. In this case, it is A. I think that's a F minus 2, D, so that's a D. In other words, it is 160 plus 13. And yep, so the checking works okay. Does everybody see how I am using the hexadecimal representation to double check the result? Okay, let me just kind of specify how I did the cross check. It is obviously a little bit out of the scope of this class. In other words, you don't have to do it this way, but I just want to show you how it is done. Okay, it is AD in hexadecimal because it's just a lookup table when you convert from binary to hexadecimal. So that part is actually pretty easy. This A means how many 16s we have. The D represents a 13 in decimal. We have 10, A is 10. We have 10 16s plus a 13, which is 160 plus 13, which comes up to exactly 173. So I will have to make a few mistakes along the way for the mistakes to have to cancel out each other, which is very unlikely. So I'm feeling pretty confident that this is the correct bit pattern. All right, so now that we know this is the bit pattern, how do we find the range of values so that when you add this unknown value to this bit pattern here, it will end up with, first of all, the overflow flag being a 1. Now that is a big deal, and also that's a big deal. That's basically, I don't have to specify anything else, actually with this case. Yep.
Well, the only two ways that we can get an overflow is if you add two negatives and get a positive, or if you add two positives and get a negative. And since
right.
we know the first one is seemed as a negative because it has a 1 in the beginning of the binary.
Mm-hmm.
So we assume that the second one will have to be also in the range of negative.
Correct. So what you're saying is, if I switch my tool to a pencil, so basically what we know now is we're dealing with a non-negative value here, and that's given to you. So the only way you can generate the overflow being a 1 is to add two non-negative values, ending up with a non-negative value. Is that making any sense? Okay. Yep.
Make sure 0B in front just shows that the number is positive.
It's binary. 0B means when using base 2. Okay, now I think I understand what your question is. Your question is answered like this. 173 is the same as 0B 10101101, which is 0x80, which is also negative something. Now, what that negative something is, how do we know if I want to interpret this bit pattern as a negative value, what is the magnitude of that value? You just take 2's complement again, it becomes a positive number that tells you the magnitude of that negative number. Okay, so we'll open up this end here. So we apply 2's complement to the bit pattern 10101101, which is the negation of the bit pattern plus 1, and that turns out to be 0B 01010010 plus 1, and that turns out to be 0B 01010011, And when you interpret this number, as a decimal number, it is 53, which is 5 times 16 plus 3, which is 83. So that means the original bit pattern is representing negative 83. Okay, I'm trying to align the number here. Is that okay? Is this part okay? Because this is actually what I'm really testing, is whether people can equate. First, start with a decimal non-negative number representation, translate that into a binary representation, and then go all the way back and say that, okay, if I want to look at this bit pattern as a signed integer, it actually represents negative 83. Is that okay? Because that part is a very, very important concept that we have to understand in this class. Yep.
I didn't interpret it as a negative number. I left them as unsigned numbers. And I asked you during the test, and you said that was okay. So is that okay?
Well, what is okay is it has to give me the flag pattern that I'm looking for. So as long as you can give me the same results, it will still be okay. Okay, now that there are different ways to work out this one. Okay, now that we know that the number or the bit pattern of 173 is also representing the value of negative 83, what do I do to make it quote-unquote overflow? Well, one thing we also know is this second number has to be negative or positive? It has to be negative. So we are actually trying to make it so negative by adding two negative numbers that it exceeds the range of values that can be represented as an 8-bit signed integer. What is the most negative value you can represent using an 8-bit signed representation?
Negative 128.
Negative 128. Okay?
Or 225. Or 255. That's looks positive.
No. 255 is represented as 1111, 1111 in binary, which is the bit pattern that represents negative 1, which is not even close to the end of the range. So at the end of the range is negative 128. So now you just have to figure out 128 plus 83 is going to be the last value that you can specify in the underscore portion. And that turns out to be math. Arithmetics, I hate it. 45?
45?
Yeah, it looks like it. Negative 45. So negative 45 is the last value that you can use in place of the underscore without overflowing. So if you want to overflow, that means you have to start with negative 46 and then all the way down to the most negative value, which is negative 128. Okay, so the range to overflow is negative 46, which is the first value that will overflow it, to negative 128. Okay, but I'm not feeling so confident that negative 46 will do the trick. So what do I do?
Check it.
How do we check something like that?
It's turned into binary.
Okay, so negative 46 is the 2's complement of the binary representation of 46, right? Because I'm claiming 2's complement is doing exactly what negation is doing. So if I use negation here, I can replace the negation with a 2's complement operator, and it will still end up with the same result. 46 is represented as 32 plus 8 plus 4 plus 2. So if I want to express it as a binary number, it would have 0, 128, 0, 64, 132, 0, 16, 1, 8, 1, 4, 1, 2, and 0, 1. Are we doing okay so far with this? Okay. And to make sure that we understand this is a binary number, I use the 0b prefix. And then we convert that into the negation operation. I'm just going to jump a few steps here, so it becomes 1101, 0001 plus 1. this is a binary number, and that becomes 0B11010010. Okay. So now the question is, if I add, okay, I'm just scroll a little bit here. So the question now is it going to overflow? 0B10101101 plus 0B11010010. Is that going to give me the flag pattern that I'm looking for? That's the question.
Yes.
Yes.
Well, we'll go ahead and find it out. Okay. We have
1.
okay. I'm not using a fixed size font here, so it makes spacing a lot harder than it has to be. So I'm gonna use fixed spacing. Okay. Now I have to fix the other one. Easy enough. All right. So this makes it a lot easier to align the bits. This is a 1, 1, 1, 1, 1, 1, 1, 0. Oh, 0. And then we have a carry of 1. What about the overflow flag? Is the overflow flag going to be set in this case?
Yes.
The sign bit is 1, sign bit being a 1, sign bit being a 0. So the overflow flag will in fact be set. So I know that 46 will, give me the bit pattern or the flag pattern that I'm looking for. You can do the same thing to negative 128. Negative 128 is easy. It's 1 followed by 7 zeros. Does anyone want to see that?
I just
Make sure.
don't think it's negative 128.
Hmm?
I don't think that's the range. I don't believe it.
Okay, let's do it. Okay, negative
you have to-
128 is just this pattern here.
Okay.
Okay, so the result of this is fairly easy. Okay, we get everything back the same way, for the least significant 7 bits, because the other number is just all zeros. But for this particular bit, what do we get?
0.
We get a 0, and then we have a carry of 1, and the overflow is also a 1.
But we
as a
can't
result.
go beyond that.
If you go beyond that, okay, what do you mean by going beyond that? Because going beyond that, do you mean 1
So
0
how-
0 0 0
here's how
0
I-
0 1, or the
So
opposite direction?
How I was looking at it was the wheel, and you're overflowing to positive 127, and then I took the range as 127 all the way to 1, but not including 0 because the 0 flag is set. So that's 126 numbers. If you add negatives to, that would turn out to be positive.
So what did you write as your answer?
Well, I wrote something higher than negative 128, which is probably the issue because we're...
Well, it may not be an issue depending on what you're saying. Because if you specify, one end of the range as 128, I have to take your answer as correct. Because 128 as an unsigned number represented by a bit number is also the same bit pattern. So I have to take 128 as one end of the range, and if you convert this value into its unsigned representation, you can also use that as the other end of the range. Because at the end of the day, it is not positive, negative, and stuff, octal or hexadecimal that counts. It's the bit pattern that counts. So as long as you're specifying that bit pattern, whatever representation you choose, hexadecimal, binary, decimal, signed, unsigned, it really does not matter. Okay, so you may still have it right. It's just that you have to use specify the same bit pattern in this case.
Yeah, I think I was just looking at the range on the other side of the circle.
Okay.
From 127 all the way to 1. So I was, do you understand? That's not making sense. So on that circle that you have, you have 0.
The number wheel.
Yeah. 1, and then it goes to 127, and you start at negative 128 all the way back to negative 1. So if I had, my number was 181.
181?
Yeah, which I found to be negative 75.
Well, Well, the question is this going to become 181?
No, it's 210.
210? Okay.
Well, there's also 4 forms of the test, so his method might be sound, but the numbers might be different or different provided starting values.
Yeah, but
I did it totally different as well. Much like yourself, I didn't treat him as signed values. I just treated them as unsigned. Had my starting bit pattern. Remember to use the flags as a starting point to say, here's the most significant bits of my solution set that I know of, and treated everything after that as an X.
Yeah.
And then all zeros would be a starting, and then all ones would be an end, and then that would be your inclusive range.
Right.
And they're written down, and they're larger than 127. Like I have 192 to 224, but then it's just the bit pattern. It can be interpreted as signed.
But it does boil down to the same bit pattern though.
Yeah.
Yeah, it's just different ways to get to the same solution. Yep. Go ahead.
What if we assumed that we were supposed to set a flag or we weren't, so we got the wrong answer, but our answer reflects that we were trying to set a flag that we shouldn't have been trying to?
That may be a little bit far-fetched. If it is my fault, like the previous question, yes, I will have to take that into consideration. So I have to take a look first, and see how bad things are. Okay.
That looks like Frankenstein.
Okay, question number 4. This is our last one. There are 4 variants of that too. And we'll go to zoom to 125. All right, so this one, once again, is the reverse of the question in the practice test. In the practice test, I give you the typical Easter egg hunt, like in your homework assignment. I ask you, I want the bit pattern to look like this. How can I make it happen? Replace the underscores with specific values. In this one, I give you the exact opposite of that. I give you the actual code. I give you the initialization of memory. And then you have to tell me what is the value of EAX at the end of these, the sequence of instructions. So, but it's really asking the same thing. Do you know how things are represented in memory and know the addressing mode well enough to figure this out? That's basically what the question is. So the first thing we have to do in this case, just like with all your homework assignments, the 2 Easter egg hunt homework assignments, the first thing you have to do is to figure out what is initialized in memory first. So what I will do is I will go ahead and just list all the bytes from in individual bytes, not 4-byte sequences, but individual bytes from the first one. Okay, the first .int is 0x25. Okay, so that boils down to 4 bytes. The first byte is 25000000. Because it is using a little endian representation, the least significant byte, which is a 25 in hexadecimal, is the first byte. Are we doing okay so far with this one? The second .int is 2500, so that means the least significant byte is a 00. The next one is 25, and then the most significant 2 bytes are 00s. The third number is 0250. 50 becomes the least significant byte. 02 becomes the second least significant byte, and then the most significant bytes are all zeros. Are we doing okay so far with the first row? Okay. And then we have 4 bytes on the second line, only used to represent an address. But since we don't know how the program is going to be loaded, we know that it's going to take up 4 bytes, but we don't know the exact values of those 4 bytes. So we'll just use question mark, question mark, question mark, question mark here to represent 4 locations are taken or used up, but we don't know exactly what goes into those 4 locations. And now we're onto the third row. Now this is a dot word, which means each one is only going to take up 16 bits. But it doesn't really matter because it's 22500 in this case, it's 0025 in the second case, and then in the third case it's still 50202. Because it's still using the little endian way of arranging the bytes, but these are 16-bit quantities instead of 32-bit quantities. Are we doing okay so far with the memory map at this point? if I want to circle one of the bytes, which is the one at address L1, which one is that going to be?
First set of question marks.
Okay, the first pair of question marks is L1. Very good. So we'll just circle that because it is special. The bookmark is on this particular byte. All right. So now that we know this stuff here, what does the first instruction do? The first instruction will copy L1 to EAX. In other words, EAX will now contain the address of this byte here. Is that making any sense? Okay. So what I would write here is EAX equals L1. Not $L1, but L1 itself. What does the second instruction do? The second instruction is move indirect from EAX to EAX. In other words, I will look at EAX right now and treat it as an address. Go to that location, grab not only that byte, but also the 3 bytes following that single byte, and copy those 4 bytes into EAX. What turns out to be at that location? L1 minus 4. So after the second instruction, L1 EAX equals L1 minus 4. Is that making any sense so far? We have seen this in the MEM2 homework assignment. The MEM2 homework assignment has the same type of construct. The third instruction is going to copy 3 bytes off from, or it will start copying 3 bytes before where EAX points to, and copy 4 bytes starting with that location to EAX. So where am I copying from? L1 minus 7. So now we can say EAX is the same as dereferencing L1 minus 7 if you want to use C terms. And that location turns out to have what content? What will be the value ending up in EAX?
0, 2.
Okay, let's do some counting here. This is L1 minus 1, minus 2, minus 3, minus 4, minus 5, 6. This is minus 7. Okay, so this 25 is L1 minus 7. What will be in register EAX? What is this 25? 25 is the least significant byte of EAX, or is it the most significant byte of EAX? It's the least significant byte because it's the first byte or the byte at the lowest location. So in EAX, we'll be having 50000025. So it will be in hexadecimal 50000025. Is that okay? Because this step is a little bit tricky. Is that okay? What is the next instruction doing? What is the operand? What is the type operand? What is the type of the first operand? It's a direct operand. It's a direct operand because it doesn't have any registers, doesn't have any parentheses, doesn't have a $sign, so it is just a direct operand, which means we are dereferencing L1 plus 5 and copy 16 bits from starting with that location to AX. AX turns out to be the least significant 2 bytes of EAX. Okay, so that means AX is the same as dereferencing L1 plus 5. L1 is here, plus 1, plus 2, plus 3, plus 4, plus 5, and this is plus 6. So plus 5 and plus 6 are copied to AX, so AX becomes basically all zeros. And as a result, EAX becomes 0x 50000000 at the end of the 4th instruction. Are we still doing okay with the instructions at this point? Now you can see how I can only ask these questions, given that you do not have a computer in front of you and can run everything through GDB, right? If you can use GDB, what do you do?
Test it.
If you can't use GDB, you put a breakpoint here, assemble, link, and run the program, and then you say IREAX at that location, and you're done. But then you don't have to actually understand how memory is laid out in this case. All right, so here's the last part here. AH, which is bit 8 to bit 15 of EAX, is dereferencing a L1 plus 7. What is L1 plus 7? L1 plus 1, 2, 3, 4, 5, 6, 7. So L1 plus 7 has a bit pattern of 2, 5. But that turns out to be bit 8 to bit 15 of EAX. So EAX ends up with a value of 0x50002500. Okay, is that okay? I mean, does everybody get this part here? You know, how we can track it down line by line? Okay, yep.
I put it in low instead of high, or I still lose 5 points.
What do you mean by low instead of high?
That last instruction, instead of AH, I put in AL.
Oh, you said
I got
AH.
2, 5 in that.
I think I'll still give you. You will still have partial credit because it shows that you still know what the first operand is. You know, because that's the only way you can locate the right. 2, 5. Yep.
Are the variations pretty similar? Like, do they still end up with like 5000 something 00?
They can be. The pattern can be slightly different. So instead of 2, 5, you may get B5 or B10, BA or something like that.
It should still be look pretty much the same exact.
It should be very similar. Is yours like completely different?
No.
Okay. It'll still be very similar because I still want to test the same thing. It's just that I don't want it to be identical to all the other variants. All right. So 4 questions. Yep.
Okay, so back when you moved it into the register, you flipped it into Little Endian again when you already had it in Little Endian. Is that right?
Which part?
Which 500000025. You started at 25. Shouldn't it just be 25000050 because they're already in Little Endian?
I still don't understand which part of the.
Move the -3 into EAX.
This part here?
Yeah. So you flipped it again into Little Endian in the register. You see what I'm saying?
Well, in the register, it is.
Don't
Because
you just copy byte for byte into there, but you would read it as Little Endian if you're reading.
Because
it
when you look at EAX as a 32-bit register as one single chunk, then the convention of writing a number is the most significant portion is on the left-hand side. So that's why when I write it as a 32-bit number, I have to put a 50 on the left-hand side because it's because of that. Does that answer the question? Let me just kind of go through this again, make sure I don't.
Is the bit pattern 25000050?
Okay, L1 -7, -1, 2, 3, 4, 5, 6, 7.
Yeah.
So this 2, 5
it's already Little
becomes
Endian.
the least significant byte
Right.
of the register.
Right.
And this 50 becomes the most significant byte
Right.
of the register. So that's why when I look at the register as a 32-bit number, it is written as 50000025.
Right, as a 32-bit number, but not
As
in
a 32-bit number.
Not in the register though. Not the bit pattern in the register, right?
Registers don't store things in the it's the literal value.
Well, my point is, like, if I wrote it down at the very end, the answer, as if it was like how it copied it in there, it would be reverse of what you're saying. But so, like when I'm doing my homework, if I put that in there, it would come out wrong. What I'm saying, it actually copies 25000050 into the register like that.
Correct.
But if you're reading it as a number, you'd have to start at the other end and read it
Right.
back.
Right. Because when you print EAX out using IR EAX or print $EAX inside the debugger, that's how the number will show up.
The 2500.
It will show as 50000025. Because the convention of writing a number is the most significant digit is on the left-hand side, but when we list memory content, the byte at the lowest byte, the byte at the lowest location is on the left-hand side, and therefore the confusion, because when we list memory byte by byte, we use that convention, but when we write numbers, we use the other convention.
So if when you're correcting this, you see that we wrote it that other way, even though everything should be in the right locations, kind of, but it'd be backwards.
You could not have picked up the 50 from anywhere else, because the 50 has to be picked up from here,
Right.
And you cannot pick up a 2.5, on the other side. So I can see how you can get partial credit, when you write it in reverse, because you can still locate the correct, bytes to copy. It's just that after you copy it, you print it out in the wrong way. You can now you can see how painful it is to grade something like this.
It's writing it actually as the bit pattern is. It's just not the decimal interpretation of it, kind of thing. So
it's not how EAX is going to be printed in the debugger. Yep. Because there are like 20 gazillions ways to make it partially right. So grading is going to be an interesting process. All right. So are there any questions at this point, other than what is the last drop date? Ouch.
Yeah, I think I see what you're saying.
I think there'll be a lot of partial credit.
I've never written it backwards again.
Yeah, it seems like it's happening twice. It really does.
Happening twice? What do you mean?
If it's little endian, you write it little endian one way and write it
the way
again.
you're writing it out,
translate it.
the way you're writing it out initially, you're flipping it initially. So dot end 0x25 is 2500x0000. That's flipping it initially. It's a little endian, right?
Yeah.
Yeah.
And then when you put it into EAX, you're flipping it again. That 25 goes to the least. So
Yeah.
what he's saying is, why do I even do little endian if initially it's going to be flipped anyway, and then I just put it into the register?
Yeah.
that way?
Because
Like, I just flip it and flip it again.
if you don't do it this way, you will be copying the wrong bytes.
Right, you can copy the wrong bytes that way, but all I'm saying is actually if you go into your debugger and you tell it to give you that first value, the
Yep.
first value will actually be 2.5. Right?
If you do an X, which means you're dumping from memory, yes, it will list 2.5
Right.
first.
So that's
But
like
if you
if you tell it to dump so many bytes,
right.
And then if you list it that way, it'll list 2.5.
But when you display EAX, it will still display 50 first. Because EAX is a 32-bit register, and as a 32-bit number, we list the most significant byte first.
Within the register itself.
Uh-huh.
Okay, if I moved, 4 bytes into, say, a 32-bit register like EAX,
Uh-huh.
and I took them directly from memory, so they were stored in little endian, and then I looked at not the overall value, but the order of the bits.
Mhm.
Would that be the same as storage in memory in little endian?
Okay, let me answer that question with this illustration here. Okay, so I'm just going to illustrate this with a dot byte.
Because I know
Okay.
you flip it when you interpret the whole thing, but as far as how it's stored in byte, 4 byte in order in the register, not memory, but in the register.
That's a register? Well, inside the register, there's no such thing as the ordering of the bytes.
Well, you still have, like AH and AL.
But there's no low byte versus high byte, because there's no inside the same register in EAX. There's no such thing as this byte has a lower address than the other byte. They don't have addresses anymore. So the whole discussion of endianness inside the same register, inside a single register, really does not apply because there's no addressing within the bytes of a register.
Right, so then I'm right. So I'm not wrong. I'm just trying to...
Just making sure we
I
have
could
this
have
correct.
listed it any way I wanted to.
Yeah.
0000000. There's a 2.5 and a 50 in there somewhere.
Next time I'll just say,
Print a soup.
print the number as the GDB would have. And there's only one answer. Black and white, clear cut. Hmm?
I said, but it wouldn't be fun to grade center.
Oh, it would be easier to grade in that case. Not what I'm looking for. But in this case, I will still give you partial credit because when you print the number, you always print the number using the most significant byte on the left-hand side. That's just the convention. But I can still see that you can get the right byte patterns into it. So you get partial credit because you know which bytes are being copied, but you're listing it incorrectly inside the register. Okay. So are there any questions about the exam itself? No questions?
What is the grade?
Sorry? It'll be similar, but not the same because with the second exam, we'll be using what we are teaching right now for the second exam. So the second exam will basically be related to translating C code into assembly code. And because you're not going to run GDB or anything like that in during the class, I will have to ask those questions in a way that can be handled inside the class, and you're doing it on paper. Sometimes what I would do is I would just write the code. I'll give you the C code. I'll give you the assembly code, and then you have to fix it. I will tell you that something is wrong with that code. What is wrong with it, and how do you fix it?
What if there's more than one thing wrong? You just gotta fix it all.
You have to fix them all. I asked that question last year. I will show you the exam 2 from last year. It was a nightmare to grade because I have to look for everything. I have to do a 3-way diff in that case, to look at to examine all the questions, because I have the right answer, the hidden right answer. I have the question itself, which has intentionally messed up instructions. So there are 2 files right there, and then I have the answer from each one of you, to attempt to fix the problems. So I need a 3-way diff to look at, the actual, answers and see whether your fix matches, what, the fix is supposed to be. That was a lot of fun last year. Okay, so that is that. How about the homework assignment? How are you guys doing with the homework assignment? What homework assignment? Okay, let's take a look at the homework assignment first. And for those of you who are having problems, doing this step by step, the worst thing, the absolute worst thing anyone can do with this homework assignment is to try to write it end to end without testing. Okay, so I can do all this translation, in my mind, and I don't need to test it. You end up with a, I guess this will be more than a 50-line program, all written in assembly without testing anything. And then when anyone writes a program like that and try to run it, it's not going to work. I cannot make this work. I cannot possibly do this homework assignment in one single pass. So my tip, my advice to people who want to get started with this one, and do it in a manageable way, is to do the translation in C first. In other words, don't even go into assembly level translation until you have translated this one into a conditional statement with a goto, and put a label somewhere. Translate this one into a whole big mess of conditional statements with labels. But because you can test that easily, okay, as long as it is a C program, you understand what it means, you understand how it is supposed to work, and then you can test and debug the program. Once you have it boiled all the way down to if x is less than 0, or if x is greater than or equal to 0, and so on and so forth like that, things that you can easily translate into assembly instructions, then start your translation into assembly at that point. But before that, test it in C. Everything can be done in C first. Do the very last, do the translation to assembly code as your very, very last stage. Does everybody get the concept? What I just talked about? No?
Yeah.
Yes?
Yeah.
Okay. I can give you one example, even though you guys all nodded your head. I just want to give you one example here. It's got just a little freebie. Okay, I'm going to use mousepad here, and I'll go ahead and just translate a little bit of this chunk here. Obviously, I'm not going to do the entire thing, but I would do just a portion of that. Okay. So when you see something like this, it looks really hard to translate because you have, you have a conjunction in the very inside, and you have negation and all kinds of stuff here. So what you want to do is to do it step by step. The first step is to say, okay, I want to turn this loop into labels and a conditional statement with a goto. Nothing more than that. So what you say is, this is loop begin, and then you have loop end here. And then you just copy and paste the entire block down there. Okay, between loop begin and loop end. And then you also have to remember that you need a goto to loop begin here, because this is a loop after all. And then on the top here, you just have to say, if this condition is false, I'm going to loop end. So what you say is, translating that into C is if blah blah blah, go to loop end, and that whole thing turns out to be the negation of this mess here. And then you test your program.
Thanks, that solved all my problems.
What? And then you test your program.
Oh, I can't believe it.
Okay, so let's just say that you test the program, it behaves exactly the same way as before, when you have a structured loop. Then what you do is you look at this entire thing and you say, oh, there's a negation on the very outside and there's a disjunction in the very inside. So what do you do in that case? You have two choices. You can either apply De Morgan's law and turn the negation plus a disjunction into into a conjunction with individual negations. I'll write it down so that you know what I mean. Or you can just do it step by step, because you can deal with a negation, and just translate it into conjunctions. So I'm going to do this step 2, another freebie. Okay, De Morgan's law says something like this: not A or B is the same as not A and not B. Does that make sense?
Yeah.
Okay. Not the entire thing is A or B. It's really the same thing as saying not A as one thing and not B as its own thing as well. Does it make sense? Kind of. For those of you who are not convinced that this makes sense, you can also do it using a truth table. Use a truth table to convince yourself. What that means is, A can take on a value of true, B can be true. If A and true and B is true, what is not A or B? The whole thing is false. What is not A and not B? False as well. What if you have A being true, B being false? A or B will still be true, not A or B, not true is false. And because you have one side, A being true, not A is false. If you have one side being false, the entire conjunction is false. So you can apply the same way the same reasoning backwards and say that it is also going to be false and false. So the last case is false, false here. A is false, B is false, A or B is going to be false. No, A or B is false. The negation of that is going to be true. Not A is true, not B is true, true and true is also true. So that basically proves the De Morgan's law. You can translate something that looks like this, which is what we have here, into something that looks like that. Are we doing okay so far? Okay. So that means I can now do another translation. Now revision control will be very, very helpful here, because you can actually track your program as you make changes to the program. So here we can now take care of this negation. Well, all we are doing is moving the negation. I don't have VI here, so it gets a little bit hard to read. I think this is the right place to put a not. And then this would be a good place to change it to an and then put another negation here. Are we doing okay in terms of concepts? Okay. So now what do? We have a conjunction to deal with now. Does everybody still remember how to deal with a conjunction and reduce that using additional instructions? Additional statements? Okay, I'll just keep this one here. I would test it first. After each transformation, test it. Okay, GCC, and then run the program again. And it doesn't take long to test it. To verify the program is still behaving the same way as before. Okay, so after that, you make more modifications. So in this case, we are going to take care of the end. Okay, so we'll basically convert it into 2 conditional statements. And the 2 conditional statements will go like this. If the negation of the first condition is true, then we know the entire conjunction is going to be false, and therefore we can get we can go to, the entire thing is false. So we can continue execution. So we go to continue, and the continuation label is going to be here. Yep.
That's applying that short-circuited and logic thing. Like if the first part of it is true, then, or yeah, the first part of it is true, then you can carry on.
Right. So basically, each step, but you can find a transformation that we talked about, for each transformation that I'm doing here. So you just have to do it step by step. But the key is don't do any assembly language translation until the very, very, very end. Okay? When I say the very, very end, it means when you have only this remaining inside the condition, or something that looks like this inside the condition, then you can convert it into assembly language. Okay? So do we have any questions here about the approach to get this problem done? No questions? This is all good? All right. We have 2 more days to do it, okay, which is not a whole lot of time. It's not really the concept that is going to get people in this case. It's the tedium that will get people in this case, because it is all in the details. Yep.
Besides the jump instruction notes, are there any other particular resources, like lecture days, that we should be looking at for specifically like the big chunk there?
The big chunk there? You mean how do you reduce the big chunk?
Like, will we be able to find everything we need to know in the jump instructions, the notes for that, or will we be?
Yes. Let me go back and refer to the notes that will be helpful in this case. There are 2 versions of the notes. They are really about the same thing. So I would refer to Control Structures 1, which is the updated version of the notes.
Is the other one the one that's in the PDF? If it's not nearly as good. The one that says good, the one that's not _1. Is the other one that one that's in the PDF?
I think this one is gonna. This is the one. This is the newer one.
Yeah.
Okay, so to answer your question, the first thing you want to do is to take care of the loop first. So the first thing you want to do is to take care of the loop. So you want to look at a pre-checking loop in this case. In other words, when you see a while loop, you turn it into something that looks like this. The C here is really just this condition. In our case, it's a big, huge mess.
Yeah, that's exactly what you were just doing.
Exactly, yep. In other words, you have a lot of copying and pasting in the process. And also, every time you do one transformation, test the program again. So then, but the problem with this homework assignment is, this condition C is not simple. So you have to also read this portion here to understand, when you have a negation, how do you take care of a negation in general. But if you use De Morgan's law, which I just did, then you can bypass this, and basically you can push things around a little bit, so you don't have to do all these steps, the tedious steps. You can shortcut some of these steps. And then when you see conjunctions, then you can do it like this. Or you can just do it, using your general logic. That works too. Yep.
So you're not looking for any specific solution. It's like the way I plan to tackle this is look for all the reasons that you get out of the loop. And
that works too.
Just like have like a big long string of
that
stuff.
Works too. Okay. In other words, okay, that's a good question. What he just asked was, do we have to do it using this mechanical transformation process, or can we look at this code using a more human perspective and just say, okay, if I were to translate, okay, let's go back to the code. Where is it? Okay, it's gone. No, it's still there. I have not closed anything yet. Okay, so the other approach, is basically to look at this chunk, this big chunk of logic here, and then you say, okay, when do I get out of the loop, or when do I stay in the loop? So as long as you can translate that, it's good. yeah, what I described in the notes is basically a structured way to do it. So you can do it step by step, and you can test every step along the way using a C compiler, and that's the advantage of that approach. But your approach, can also be tested using a compiler, because what you do is you just take your translation and compile it and see if your program works. Okay. Are there any other questions about the homework assignment? Are there any questions about how do I compile this code that is written in C?
Do you need comments in there or anything, or just
Comments is for yourself.
Yeah, I know, but like you did last time, you commented out the C code. Like, do you just want assembly code in there?
Just assembly code is fine with me, but I think having C interleaving the C code will be helpful to you in the debug process.
What about to you?
To me, as long as I can at least identify which part matches which portion of the code, it'll be fine. I can, for the most part, tell which part is which part, because I can analyze the structure of your code and figure out, okay, this is the part that does this in C. Yep.
Can we send it as, say, ODT document, so it would be color-coded like this is the comment, this is the actual code?
No, you have to have your assembly code. You can have files in addition to the .s file that is your assembly source code. You can have additional files, but what I'm looking for is division.lowercase(s). That's the file I'm looking for, and that's the file that I will assemble and link and run to test your code. Now, are there any questions about, how do we translate this into an actual program and test the program? No? Copy, paste, put it inside main. And if you want to test different values, my recommendation is not to hard code it inside the program, but to use GDB to help you. Because you can, this is the other thing, I almost forgot. In GDB, you can change memory locations so that you don't have to hard code anything into the .ins to test different values. Okay, so I will just do this as one little quick thing here. Okay. Okay, so what I'll do is I'm just going to write a very simple program. Okay, so I just use move.s as a simple program. In here, I have .data. I have x as .int, let's say 6 here. This is going to be useful for debug purposes, so I just want to cover this part as well. I will have, okay, this is the exit code already. All right, so your program is going to be like pretty long, but you're going to depend on the value of x, right? So what you want to do, okay, let's say I have a move instruction here, moving the value of x into some other register, let's say ECX here. Okay. So to test this program, the way it is set up right now, x is going to be 6 all the time. Every time you run this program, the value of the 32-bit inside x, or starting at location x, is going to be 6. Which is not very useful when you're testing a program, because you have to feed it different test cases. So, but I don't have to recompile or reassemble the program to test it with different test cases, and this is how you can do it. As I'm hoping that you guys can type, at least as fast as I do now, because with all the homework assignments and all the practice, now we can, do write all the commands just as quickly. Okay, put a breakpoint on line 8 here. Okay, and what you do is you just run the program, at least up to the point where you will start to use the value the first time, and then what you do is you say set x equals to a particular value. So if I want to test x being 32, I will set x as 32, and then when I single step the program, I would check ECX, and ECX becomes 32, because set x equals 32 actually changes the memory content at label x to become 32 as a 32-bit number too. Okay, now I think this can come in very, very handy when you're testing programs like these, so that you don't have to go out, change the source code, hard code another constant in, and then run your program again. And for those of you who want to script everything, you can actually use GDB, as a scripting language. When you not help man GDB, it shows you how you can use GDB. One particular option you can use is to specify a script when you start GDB. And I believe that is, you can specify -x commands, that's just a list of commands. You can pipe it in, okay, and now remember, you can just use redirect. Okay, I will show you exactly what I mean by that. Since I already have those commands here, yeah, I'm running a little bit over time because I think I cut short the class a few times also, so it all evens out. Okay, but this is going to be useful because it is very, very helpful to be able to do regression testing. Okay, because you can save all your test cases so that you can use the same test cases over and over again. So what you can do is in the text file, just type the same commands that you would normally use when you're debugging a program. You can set a breakpoint based on the line number or the label. Okay, I would use the label because you can, when you work on your program, the line numbers will change, but the labels stay the same. So you can say L, put a breakpoint, B at loop begin. So that way it will always put a breakpoint at that label. But in this case, since I don't have loop begin as a label, I'll just use breakpoint at line 8, and then I will run the program, and then I will set x equals 32, single step, print ECX, and I will call that my script. Basically, these are the very same commands. Other than I didn't use print ECX, I used IRECX, which that's the same thing. So now I have all my commands put into a text file. So I can now say GDB MOV, which is the name of the executable, and then redirect the standard in from the file called test.gdb. And it does it. It just did it so fast, that I did not. It took me like 2 seconds to figure out. Oh, did it happen? It actually did happen. It did not echo the command itself, but you can tell from the feedback that it set a breakpoint at a certain location, and the run actually start running the program. We hit the breakpoint on line 8, which is as expected, and then we set x to be 32. And that's the output of the set command. And then we examine, oh, I take it back. No, that one has no feedback because when you set the value of a variable, it doesn't give you any feedback. And then we single step, we stop on line 10, we printed $ECX, and that's the result of ECX. Okay, so every time you make changes to your program, you recompile your program, and then you just run this command again, and you just have to make sure that the output of your debug session is the same. And for those of you who want to be fancy and put loops into the script and stuff like that, the GDB scripting language actually supports subroutines and loops and other fancy stuff. So you can make this very, very fancy if you want to. But this is already useful. Okay, I think this is also very, very useful. Okay, any other questions about the homework assignment? Do not procrastinate. Alrighty, so I'll see you guys over at the lab. For some of you who go to the lab, I'll see you over there.